Yeah. Because I can't make it in Swedish. No Chinese. Vielleicht kann ich auf Deutsch probieren zu sprechen, aber English should be better. Okay, so the first talk was a reminder on arithmetic intersection numbers. And for the second talk, I'll start with defining what I would call the height of a variety and give some examples. And then try to explain the theory of Outbreak Matrix due to Zhang that allows to bring in the theory limits of heights defined by Hermitian line models. So, chapter 2, the height of a variety. And before I pass to chapter 2, I need to put on an erratum to yesterday's talk. In my definition of Hermitian line model, which was a pair of a normal plus a metric, one needs to assume that the metric is invariant under complex conjugation. So on X of C, you have a complex conjugation, which is an anti-holomorphic map, and which is just given by if you make a complex to scheme, you can just with the morphisms from spec C to spec C, which is induced by complex conjugation, and then you get a anti-holomorphic map, and one assumes that norm is invariant on the complex conjugation. That's some hypothesis that is always assumed in the theory of Gillet and Soulet. And actually, I tried to look at the paper and to see where the hypothesis is used, and I couldn't track it down. So I don't know where it is actually used, but it must be used somewhere. And it's probably hidden in the stuff like moving K1 chains and so on. I mean, there are very subtle parts on the paper which are pretty much ignored at first reading and also at second reading, apparently. Okay, so the height of variety. So here it's just to introduce a notation, because we take X as yesterday, proper and flat over spec Z, and L bar Hermitian line model on X. And we define the height as follows. So we know that we have the degree with respect to L of X, which in fact will be the degree with respect to LQ of XQ, which is just take C1L on the generic fiber to the power n and intersect with XQ. And n is the dimension of XQ. So n plus 1 dimension of X. And we know that we have also this arithmetic intersection number, arithmetic degree of C1 hat of L to the power n plus 1, because X has dimension. And the standard definition is just to define the height of L of X with respect to L. Maybe I should, I don't know why. Maybe I could also write something for some, say, take Z in X, which will be also proper and flat. And the dimension of Z equals G. And now I will put Z for that. So maybe and the height of Z with respect, and Z is irreducible, will just be the height, the arithmetic intersection number divided by d plus 1 and the degree provided the degree actually I don't care about the denominator vanishing because usually one so usually LQ will be ample on XQ so that the degree Q of ZQ is strictly positive. So that's okay. And there is one factoriality property which is important. Is that the height with respect to here in the bar with respect to f upper star of z is just the height with respect to L bar of, which is an application of the projection formula I had stated last week. So actually, here I've written f lower star of z, but I could also write f of z if f is finite, or if the dimension of f of z is also d plus 1, because here the difference between f of z and f lower star of z here and here is just a degree, and the degree is the same in the numerator and the denominator. So, and to give a justification for this denominator, just go back to take a closed point in not a closed point, but well, okay. Let's take a closed point in the generic fiber, so it corresponds to some algebraic point on XQ, and let's take Z to be the bar, the Zariski closure. And so what does it mean? With that Z, the residual field of Z is some number field. And there is a morphism from which I will write epsilon Z, like yesterday, from the spectrum of the ring of integers of the number field OF to Z, which is not really an isomorphism because this is integrally closed and this is what it can be, but it's almost an isomorphism. And what I had said yesterday that the arithmetic C1 L bar on Z, this is just the arithmetic degree of epsilon Z L bar. And C1 L 0, so this is the degree of the field extension, which is just the degree of the residual field. And so that the height with respect to L bar of Z is really the height is the normalized height of Z. So divided the height divided by the, and G is 0. And so just the height divided by the degree, the arithmetic degree of So remember that Emmanuel had said that he didn't want to care about field extensions, and in this theory we have, because eventually we were going to study sequences of algebraic points, so the degrees will go higher and higher. And so that's an example, and I can go further through this example, and take for A an Abelian variety. No, not for A, not A. I mean, everything is called X, so let's X be an Abelian variety over a number field F. And assume that that it has good reduction everywhere, so that there is an Abelian scheme X over OF that extends X, so which is a model of and I take a line model L on X, and then there is essentially I will need to make something. I will take O, which is in X of F, which is the origin. I will, well, and there will be essentially a unique extension. And how is it unique? What I fix is that I fix a basis of L at the origin. So I take, for example, an identification of F with L at the origin. And then the origin extends to the Abelian scheme as something which I will still write O, which is just a morphism from spec OF to curly X. And then I will assume that this isomorphism extends to so once I fix an extension of the line model, so this is called a trivialization at the origin or rigidification of the line model, then there is a unique extension such that this rigidification extends. And now for the matrix, I have not prepared the formula, but from the theory of Riemann forms, one defines a canonical matrix. So L sigma for sigma homomorphism from F to C. A canonical matrix, just look at how there is a complex description of line bundles on complex tori. They are given by automorphic factors that are induced by some bilinear forms, which is positive definite, the Hamilton forms, which is positive definite if the line bundle is ample, for example. And you just, from this formula, you just can write down a very simple formula for the norm of a section, just taking an absolute value of something at some point, and it works well. And so this gives you a very canonical metric, and this canonical metric is a unique one. So that the curvature form of L sigma is invariant by translation. And the norm of the trivializations, I could call that epsilon, or this epsilon. And the norm of epsilon of 1 which is a norm of the trivialization at the origin, is 1. And the relation between Riemann forms here and the curvature form is that a 1-1 form on a complex torus, which is invariant by translation, is just a Hermitian form on the tangent space at the origin. And this Hermitian form is the Riemann form of the line rule. Okay, and now if you do things this way, so you have on X, this defines some L bar in P cat of X. And the point that you have multiplication maps from X to X that extend the multiplication by n on the, well, which are multiplication by n on the Abelian scheme. And if you pull back n upper star L bar, example, computed. So this will be L bar n squared if L is antisymmetric. And on Abelian varieties, up to power of 2, any line model can be written as the sum of a symmetric and an antisymmetric line model. Symmetric means if I pull back by -1, I get the same, and antisymmetric, I get the opposite. Well, maybe odd or even. And so, for example, if you take L to be, if L is ample symmetric, then H L bar, which, for example, from X of F bar to R, to the real number, will be this is a Néron-Tate height. And there are properties. I wanted to say that properties of the Néron-Tate height, so I'll stop for this. And let me just give two properties. Second, so in the case of height of points, you probably have heard that the height function is up to O of 1 independent of the matrix and the models and so on. And the same holds for heights of cycles. So let's assume that LQ is ample. Then if X prime L prime bar is another model of XQ LQ, so another proper flat variety of spec Z plus another Hermitian line model on X prime, which extends L, LQ, then the height with respect to L bar prime of Z minus the height. So there exists a constant C So in some sense, this height function only depends up to O of 1 on the generic fiber. But one of the interests of Arakelov geometry is to provide actual numbers and not functions defined up to O of 1. So that's very important for the sequel of the talks, that we actually have actual numbers and not functions defined up to O of 1. But that shows, for example, that if you want to define the height of a variety, you can make, if you are content with defining up to some bounded function, there could be other rules. And for example, Patrice Philippon has a different theory of heights, which essentially appeared at the same time as Falting's paper. Philippon observed that if you have a variety in a projective space, it has a canonical Chow form, which is some homogeneous polynomial on some degree, or multi-homogeneous, that describes on what hyperplanes if you take generic intersections of hyperplanes of the correct codimension, that they will cut your subvariety in something empty, and sometimes for non-generic it will cut in something non-empty. So there is some Chow form that describes for which intersections you get something. This is what you... Okay, and so you have some homogeneous polynomial on some degree, and Philippon says, okay, this polynomial is well defined up to a scalar, but I can take, for the height of the variety, just the height of the family of the coefficients. And it makes a series that works, and Philippon in that way could define Néron-Tate height of subvarieties, but without Arakelov geometry in some sense. More classical diophantine geometry. Okay, so the other properties is a finiteness theorem. It's if you fix a number d. This will be an integer. Well, no, this will be d and h. There is the set of integral closed subschemes of x such that the degree of z is say smaller than d, and the height of d is smaller than h, and this is finite. And of course, LQ is empty. And in the theory of Philippon, this statement is rather obvious, because if you fix the degree that prescribes the size of the Chow form, you know of what degree it will be. And so the height will be the height of the coefficients of the Chow forms, and you have the classical Northcutt Theorem that tells you that if you will get finiteness for it. And actually, one of the proofs of this finiteness theorem in the paper of both Gilles and Soulet goes by showing that this height, or that height, is related to the height of the Chow form, and using that comparison. And so applying classical Northcutt theorem. It depends on, this is an important question, but it depends on the choices you make.
Yeah, but if you had the standard metric on P
for that one, for the standard metric.
It's not clear, it's not obvious.
No. For that one, it should be okay. If you take O of 1, so I will come back, in fact, to this later. But if you take O of 1 with a standard metric on P and Z and the Fubini study metric at Archimedean place, then it will be non-negative and maybe positive, in fact. But one part of the lectures is to describe the interplay between the positivity of the line bundle, in some sense, and the positivity of its metric, and positivity of the height. So that's basically what Bogomolov's conjecture, the proof of Bogomolov's conjecture is about. Okay. So this is section 2. So now I want to give a second definition of a Adelic metric that is totally with Emmanuel's definition. So that's chapter 3. And this is essentially due to Zhang, except that I will give a slightly different presentation building on work of Bubler and myself. But essentially, this is due to Zhang. So S will be the set of places of Q, and so I will also always identify the finite place with a prime number and the Archimedean place with a symbol infinity, and the p-adic norm is normalized such that the absolute value, the p-adic absolute value of P is 1 over P, as usual, and you have the product formula, product for all P, for all V in S of XV. Which is the trivial so the product of all absolute values of a number is 0 if the number is 0 and 1 if the number is non-zero. So it's a trivial absolute value of that number. Okay. So now I will define analytic spaces for all, maybe not define, but I will summon them. And so for V, when V is infinity, I will write X and V, will be the analytic space at infinity, and which will be just X of C modulo the complex conjugation. And if V is finite, then XVN just be the analytic space associated to X tensor QP. So X is a scheme over Q. Maybe finite type. Associated to X tensor QP by Berkovich. So it's not the place here to give you a full theory of Berkovich spaces, because it would be too long and maybe almost, well, at some point it will make an importance.
Berkovich spaces associated with schemes were introduced by Raynaud.
Okay, good. Know everything about Berkovich spaces. That's very good. Yes, I'm sure he said. So maybe what I should write is that you have, in any case, what you need to know is that if so here I have QP, and then I have QP bar, to which the absolute value extends, and CP, which is the algebraic closure of QP bar, which is this is the algebraically closed, and this is complete and algebraically closed. And so if I take the CP points and embeds topologically in XPN, that contains the classical points or the Galois orbits. That's an important step. And why these spaces are nice and this is not nice? This is totally discontinuous. And so, but XPN is a very reasonable space. It is locally contractible, locally compact. So from topological space properties, this Berkovich compactification is very nice. And while those are counter sets, and it's hard to do interesting analysis on counter sets. Well, you can, but I will also use the fact that if I have there is a sheaf of analytic functions on XPN, which will be denoted by OXPN. And it's made for that if I have some function, some analytic function on an open subset U of XPN, then there is a norm. Naturally. And this norm extends what you could imagine. So, I mean, if F is analytic functions, at least can be evaluated on X of CP, and the absolute value will be that, but the norm extends. Is it all I need? Well, probably, yeah. And here I should also write this is the image is dense. And to shorten notation, I will sometimes write x add, or maybe x add n, I don't know, just to be consistent. No, x add will just be the adic space of x, and it's just a disjoint union for all v of xv1, the adic space. But it's not adelic space, actually. Adelic analytic space, I should write. So the topology of this space is the following one. It's just a disjoint union of copies of locally compact spaces. So you just the topology you can imagine when all copies are separated. And for example, if I take a function, a continuous function phi from x add to the real numbers, it's just functions phi. It's just collection of functions on all xvn, and if I want a with compact support, this will correspond to functions phi v from xvn to R with compact support for all v, plus phi v is identically 0 for almost all v. Because it works well with just at some point I will use. Let me write the definition of an Abelian metric. An Abelian metric will be a collection of metrics at all places, and so it's like a a function is a collection of functions at all places, and it's a function on the differential. It's just a function. It's just a collection of functions.
There is no map from point of x.
No. That's just a disjoint union of the spaces. That's a notation. I mean, if you want a map, you need to take a product and not a coproduct. But so now there are notions of continuous metric. So continuous V-adic metric on L and continuous adelic metric. But I will start from the, so continuous V-adic metrics on a line model, L, is just a datum from, if you have U in X and maybe a section S in L of U, maybe let me gamma of UL, then you want a function, a section from U to a positive function, non-negative function from U to R plus. And how is it supposed to how are all these functions supposed to behave? It's just that the norm of S restricted to V should be the norm of S restricted to V. And the norm of F times S is supposed to be the absolute value of F times the norm of S. If F is Vn. And this should be continuous. And of course, if you, for a line model, you could pick local trivialization. So if F is S is a local frame, something which does not vanish, then norm of S does not vanish. Actually, it could. Wait a minute. Okay, I need to be non-zero if S is 0. Okay, now I don't want to say this. This is a mistake in the paper. Okay. And if I have metrics on L and M, I have a metric on the tensor product. I have a metric on the inverse, and the map from. There is also what is a metric on OX, which is here. It's OXV1. It's just you have this section 1, so you just need to take phi v, which is log of norm to the power -1, and just this gives you the fact that norm of F will be absolute value of F exponent minus phi v. So finite places, there is a notion of algebraic matrix. At finite places. So let's take a model X on a spectrum of ZP. Or spec Z, what do I prefer? no, for simplicity, let's take respect Z. And line bundle L. On X, extending. And this gives a canonical metric. And finite places. And the description is as follows. If I could take an open subset U in X and a basis epsilon trivialization of L restricted to U. So it means that L restricted to U is isomorphic to OU. We will use some other input of Berkovich spaces, which are spatialization map. So P is a prime number, which goes from the Berkovich space, XPN, to the scheme X over FP. In some sense, this is just the usual way. If you have a point in projective space over Q, you can reduce this point 1P by choosing denominators and so on. And this works similarly for Berkovich spaces, except that if you take complicated points of the scheme, you will not land up to, of the Berkovich space, you will not get actual points with coordinates in FP, but actual schematic points of the scheme. So this is a map from the Berkovich space to the scheme, not to the FP points or whatever. And this map is anti-continuous. Inverse image of a closed set is open and vice versa, so that's strange. And this is where you pay for the non-Archimedean property of finite norms. I mean, you have nice spaces like Berkovich spaces, which are locally compact and locally connected and so on, but you have to pay for the ultrametric property of periodic norms at some point. And this is one of the places where you pay. You get this map, which has a funny topological property. And so this will be maybe S, is this pi P or SPS? Well, in fact, I will SPP. And now I will use a notation for tubes. The periodic tube of U is just the preimage okay? So imagine you have some open subsets in P and Z, in the projective space over Z. You have this, you take the special fiber at P, you have an open subset of the scheme, Pn over Fp, and you can take in the Berkovich space the closed subset of points that reduce to there. So for example, if you take projective line, and you take for open subset the affine space, or the complementary subset of the point at infinity, you will get exactly the point, the unit disk. So you will get the Berkovich line, and in the Berkovich line, you have the unit disk, absolute value is smaller than 1. That's exactly the set of points which do not reduce to the point at infinity. So yeah, there are tubes in that way, and this is closed. This is closed in XPN. And this algebraic metric is characterized by the fact that the norm of epsilon is constantly equal to 1 on the tube. And if you look at the standard Veil metric on P and Z, on the O of 1 of P and Z, you get that, for example, you have this trivialization x0 that is the basis of O of 1 outside of the hyperplane at infinity. And if you have a point that does not reduce to the point at infinity, to the hyperplane at infinity, the norm of x0 at that point is exactly 1. Okay. Maria, is there any question? No? C'est Gaël qui t'embête? Okay. pouvoir te laisser faire. Hein. Okay, so algebraic matrix. And now, okay, for definition of a continuous this is just a collection of V-adic adelic matrix and continuous, of course, V-adic adelic matrix at all places, but which differ from some algebraic matrix which do not differ. Okay. From some metric at finitely many places only. So it says that I say that a family of V-adic matrix is an adelic matrix if for there exists some algebraic metric and which coincides with the adelic metric at almost all places. Okay? And this is quite reasonable because one has to observe that if I take two algebraic metrics, so I have two models X on spec Z and two line models L, so X, X prime, L, L prime. In fact, by a standard result of EGA, which are in the chapter about direct inversely limit of schemes and so on, there will be an open subset, a dense open subset of spec Z, over which XL and X prime L prime will coincide. And so it means that for every place in this open subset, the V-adic matrix will be the same. Okay. And now, for example, a continuous adelic metric on the trivial line model on X is exactly a family of functions phi v. So here, for simplicity, I will assume that X is proper of a Q. I have not thought of what it should be if X is not proper, but it has no importance in Fourier geometry. So it's just a collection phi v in which will be continuous on xv1 with respect to R. And the fact is that so is phi a continuous function. So, and what I want that phi v is 0 for almost all v. So this is just a phi a continuous function with compact support on the adelic space. And phi is, so phi v is log of the V-adic norm of 1, and so phi is. So the interest of so there is a maybe it's time to write this exact sequence. Yep. So I will write peak bar of x hat, or I could write peak bar or peak hat. It's time. I think I wanted to let you hear the song of Joe Cooker. You must put your hat on, but I cannot make the choreography. So, so you have this peak hat of x hat, the set of adelic matrix of line bundles on X plus adelic matrix, And so there is a, you can forget about the matrix. You should never, but you can forget about the metric. It goes to the usual Picard group of X. And it's surjective because every line model has a metric. And then the kernel comes from describing the metric on the trivial line model. So I say that the kernel comes from continuous function with compact support of xad with R. And so here I take a function phi and to the function to X, and norm of 1v is exponential minus pv. Here this is just take L and norms and just send to L. And this map here is not injective. It's a bit subtle, but it's nice to describe the kernel. So the kernel is, I take two function phi, and I want that the associated metrized line bundle are isomorphic. So here it means that I have OX with norm of 1 is exponential minus phi, and I want this to be isomorphic to OX, and norm of 1 is 1. And how are given isomorphism from OX to OX is just multiplied by some constant. It depends on gamma of XOX. So this isomorphism is given by, say, 1 maps to A, which will be an element of gamma XOX star. And so if you want this to be an isomorphism, you need to have phi exponential minus phi is absolute value of 5. So here this space is described by the unit in the global section of the scheme. So usually these units are very small, and it must be if x is integral, this is just, since x is assumed to be proper, since if x is integral, this is just a number field by Stein factorization. But maybe that's a product of fields, and maybe the scheme is not reduced, but I don't want to. And then it's not yet injective, because if I take some element there of whose all absolute values are equal to 1, then it will give the same metric. And so the kernel is roots of unity. And then it's it. So there's a similar exact sequence in Arakelov geometry that maybe Sule described last week. Do I need green functions? Maybe not. No, I will skip that. Just a remark that might be useful later on. You've seen that for algebraic matrix, the V-adic norms are very much related to sections of the line model on open subsets. And there is a so assume that X is, I mean, the precise assumption is that it is integrally closed in its fiber. And L, and then the point is that if I take gamma of XL, I take the integral sections of a line model, and map it to of XL. And this will be injective. And what is the image? Is exactly the set of section S so that the norm of S V is smaller than 1 for every finite V. So for example, if you take maybe it's easier to understand what happens if you take the trivial line model with a trivial metric, so L is OX. It means that if you have you take some element, maybe there is a local analog, but you could take you could tell something which is like a rational function on X, and you want that its v-adic norm is smaller than 1 at all places. And this should remind you of the fact that if you have a normal domain, integrally closed domain, it is the intersection of its valuation subrings of height 1. And so the point is that if your section were not in an integral section, then there would be some valuations V, some finite place that would observe that, and you would see that the v-adic norm is strictly greater than 1 at that place. Okay. I want to give an example of algebraic dynamics. And this is goes back to Tate, Cole Silverman, and Zhang in this context. So we will assume that there is a self-map from X to X, such that F upper star L is isomorphic to LQ for some Q at least 2. And this isomorphism will be fixed. I mean, I will fix an isomorphism. And then there is a unique on L, for which epsilon is an isometry. So if L is endowed with an adelic metric, then F upper star L is also endowed with an adelic metric by functionality. L to the Q is endowed with an adelic metric as well, and so the claim is that there is a unique adelic metric which makes this chosen isomorphism into an isometry. Okay, and the proof for the proof, there are two parts. First of all, you can construct a model XL over a dense open subset of spec Z such that epsilon extends to an isomorphism such that F extends, and I want that F extends to to a map from X to X, and the chosen isomorphism extends to the isomorphism. So this is possible just by standard EGA stuff, I mean just extending morphisms. So this is standard, and this will show that if I take an adelic metric, an algebraic metric corresponding to this curly X, curly L, at a place V in this dense open subset, it will give me, it will have this property that it is an isometry at, so for V over U is this subset, the corresponding V-adic algebraic metric turns epsilon into an isometry. So the job to do is only at finite. And then what you can do from this map epsilon, what one needs to do is to look at the space of metrics on L. So L is there, and the space of metrics over there is just various choices of metric on L, and it's just the same as the metric on the trivial line bundle. So it's an affine space. So affine space under exactly the C of its V-adic matrix. And I have a self-map on this space, which corresponds to take a metric on L. You pull it back to F upper star L. You transfer by epsilon to a metric on LQ. And then you take a Q root, and you get a metric on L. And this map, if I this map is Lipschitz with a ratio 1 over Q. This affine space is some exponential map, so it means that when I take the roots, I divide something by Q in this vector space. So with a supremum norm on that space, this map is Lipschitz with constant 1 over Q, so it's a quadratic map. So by Picard fixed point, there is a unique fixed point. Okay? So now, if you hear that and if you heard about Zhang theory or Gold-Silverman stuff or Tate, you probably don't see the link, but in Tate's Gold-Silverman, Zhang, there is a limit process of taking the metric and pulling back and pulling it back once again and so on. But this is exactly what you do when you prove Picard's fixed point theorem. You iterate the quadratic map and you show that it converges to a fixed point. Good. 20 minutes encore, c'est ça? J'ai jusqu'à 11h ou j'avais 1 heure? So it's the time to talk about positivity. better to be positive. Yeah. Yeah. No, it won't be. It won't be. The image won't be. Might be smaller than that. The map is still injective, yeah, just by density. But if the image is always contained in that, but it could be smaller than that. Yeah. But this hypothesis is very minor because I can just take the normalization of X into the generic fiber, and that does not change the generic fiber, and it only takes a model which is slightly bigger, and where you see the divisors that you should see. So that's not an annoying hypothesis in the system. So it's 5. No, actually it's 4, but I skipped chapter 4. So it would be nice to have a height machine for adelically metrized line models as the one similar to the one I described for Hermitian line models and models. But this is impossible because this matrix can be slightly too pathological. I mean, one needs to take a smaller set of metrics, and you can see it at the Archimedean place already. If you remember of the definition of the height function, of the height pairing, there was an integral of the form z of c there was some integrals that way. And here, C1 L bar 1, C1 L bar D minus 1 are the curvature forms of the metrized line model. And how is this curvature form defined? It's just DDC of log of another section, S1 to the power minus 1 for S1, a local non-zero section. But if the matrix is only continuous, this DDC is not defined by calculus, it's defined by distribution theory. And it's a current of order minus 2 because I've differentiated twice. And there is no theory, well, there is, but there is no general theory of multiplication of currents for the same reason that there is no multiplication of distributions in general. And so if you just take continuous matrix and you get complicated current there, and there is no way of multiplying them. And so, and of course, there is no way of integrating this against the log of some function, which might have rather complicated singularities. And so this doesn't work. So one needs to find a theory to restrict the family of metrics that we use so that maybe not the formulas will make sense, but in some sense we will be able to approximate such formulas by smooth counterparts. Okay, and this is a theory of semi-positive adelic matrix invented by Zhang, and maybe then is an analogous theory. And so one says that XL is semi-positive. Oh. Well. So here it's an actual Hermitian line models. If for every prime P and every curve C inside X of P. So every vertical curve, the degree of C1L with respect to C is non-negative. That's the geometric assumption. And the Archimedean assumption is that the curvature form C1 of L bar is non-negative. It could vanish somewhere, and being non-negative, you remember that maybe X is not smooth. So this is a non-negativity in a very weak sense. It means that for every disk, there is a for every phi from X of C, and every local section S, I can pull back phi upper. I can pull back F, say, and take log of phi upper star S minus 1, and I will say that this will be is priori subharmonic. Well, it's subharmonic, in fact. And well, it's yes, sub. Or equivalently DDC of log phi upper star S minus 1 is a non-negative form on the disk. And a 1-1-1 form on the disk is just a function times dz bar, so with an I somewhere. And you just say that the function is negative. So that's a definition. And so this implies that on the generic fiber, the L is nef on the generic fiber, because essentially if I have a curve on the generic fiber, I can move it to the special fiber, and the degree on the generic fiber will be related to the degrees on special fibers, and it will be non-negative. So that implies that the line model is nef. And the basic proposition is that if I take two semi-positive algebraic matrix, the corresponding intersection numbers are not too far away, depending on the distance between the matrix. So I will take cells order and X prime L prime, semi-positive and in fact, there is, I need to have L0, LD, and L prime 0, L prime D. For every J, I will have the distance between L bar J and L prime bar J. This is the distance between this Hermitian line model, the distance at the place V. So how is the distance defined? I just take the log. So I have the function, it will be the supremum on xv an of the, so just say that, okay, this will be the distance of the adic matrix. I don't want to write the formula on the blackboard, but I have two v-adic matrix on Lj and J prime because they are models of the same line model. And so these two v-adic matrix differ by multiplication by a function of the form exponential minus phi vg rather, and just the supremum of phi v. And this is the distance. And there is a formula that the arithmetic degree of C1 at L begin with 0. Okay, 0 C1 hat LG bar against some cycle Z minus the arithmetic degree of C1 hat L prime 0 C1 hat L prime D similarly against the same cycle, not against the same cycle Z, so it will be Z prime. And so, sorry. Okay, so I have models of the same stuff, which are X and 9 models. And I take Z, which is inside X, and then I will have Z, the closure in X, and Z prime, the closure in X prime. So the idea now is to compare using these two models of XLJ, of X and the line models LJ, plus matrix, to compare the arithmetic intersection numbers. And the fact is that if the matrix, the Hermitian line models are semi-positive, there is an upper bound for the difference, which only involves degrees on the generic fiber and the distance of the adic matrix. And so this will be the sum for all V of delta V of LJ prime bar times times the degree. No, sorry, the sum and the sum over all G. Okay, will be sum of all J, the sum of all V of the distances times the degree of C1 L0, C1 L J minus 1, C1 L J plus 1. So I omit C1 LD against Z. Here it is. Okay. So just step back and read the formula once again. So there is an upper bound of the difference of the two arithmetic intersection numbers associated to the two models by a sum over also all line models. It's indexed by the line models J, which goes from 0 to G. And then there is the degree of the cycle Z on the generic fiber with respect to the remaining line models, multiplied by the sum of the differences of matrix associated to the two models. And by definition of an adelic metric, this sum is finite. Because by definition, delta V of LG bar is 0 for almost all places. Okay? So this is a basic and fundamental formula. And well, it's interesting to prove the formula, but maybe I should skip that. The idea is to prove that is you go one by one by using the fact that the arithmetic intersection product is bilinear. So in some sense, you can write this as the sum. So this is the sum over all J of the arithmetic intersection product of C1 at, L0 bar. And then C1 hat of LG prime plus 1 bar, etc. C1 hat LG bar prime against Z. And at least this formula makes sense if X is prime. If X is X prime, then I'm computing arithmetic intersection numbers on X, on the same model. And then I just can write this formula by using the multilinearity. if x is not equal to x prime, then I can find a common model that refines both and reduces that case. And now the point is here, this is the trivial line model on the generic fiber plus this corresponds to the trivial line model, well, to the metric on an algebraic metric on the trivial line model. Which has a section 1. And I can use the section 1 to compute. I mean, I can put this at the end and use the inductive formula using that line model. And if I do that, I have that there appears and so here I am removing some terms somewhere, and here it's C1, it's L's, and here it's L primes against the divisor of 1. So it's maybe it's 1 will be, I should write Sj, and plus integral on, and integral where? What do I want to write? Okay, on the log of Sj minus 1 times the arithmetic. And the point is, this is positive, because the product of positive 1-1 forms is a positive 1-1 forms. So this is a positive measure, and I will integrate a function against a positive measure. And so it is just bounded from above by the supremum norm of that, which is just the function phi infinity, so phi j infinity, because it's on set of C, which is just bounded from the supremum norm, the distance of the Archimedean metric, times this. So I can bound that from above by the distance, and I get the integral of this form, which is just a degree. And here, the fact is that I have similar estimates, because this divisor is bounded from above and from below by a similar, it's bounded by the sum over all p of something like delta p and the special fiber of Z. And so and since this is an F, those are F line models on vertical fibers. If the geometric intersection product, because this will be geometric, will be bounded from above by this times what it is generically, and this is what I get. And so now that shows that if, from that proposition, you can see that if I have semi-positive metrics converging uniformly to some adelic metrics, and by uniformly I will mean that outside of a finite set of places they don't move, and at each site, at each finite places, at each place they converge uniformly, then the corresponding arithmetic intersection numbers will converge to something. Just because, just extending some continuous function. So I lost my brush. Here it is. So the conclusion is that no, maybe I did a definition. An adelic metric is semi-positive if it is a limit of a semi-positive algebraic matrix. And the topology on remember that the topology, the set of metrics on a given line model, this corresponds to the set of compactly supported functions on something. So the topology of convergence on this set of compactly supported functions is that outside of the compact set, it's constant. So this is really the correct topology of this set. And so the corollary of the proposition that there exists a unique pairing from so semi-positive metric, then I need to take d plus 1. So I take cycles of dimension d on the generic fiber. I take d plus 1 line models on X with adelic metrics which are semi-positive, and I get a real number, and that extends, so which is continuous. And extends the arithmetic intersection degrees. Okay. Just I take a sequence of metrics which are algebraic and semi-positive and which converge to my matrix, and can compute the arithmetic degrees against any given cycle and pass to the limit. And now here, so this will be, here it's only, it's not a subgroup. I mean, this is multilinear, but you can only add semi-positive metrized line models because there is a condition of positivity that does not pass to differences. But then what Zhang did is to define admissible metrized line bundles is just differences of semi-positive one. So Zhang calls this calls them integrable, but for a reason that will be clear on Thursday, I do not want to call them integrable. In fact, because I will look at functions, metrics on the trivial line model correspond to function, and I will say that a function is admissible if the corresponding metric is admissible. And I do not want to say that this function is integrable. And this is rather, it's not a question of integrability. This is rather a question, for example, this theory has a complete analog in complex function theory. And this will be, I hope, clear in Romain Desjardins' talk. I mean, these analogs of this estimate are well known in work of Bedford-Taylor and de Mailly, complex analogs. And for example, these admissible functions or admissible metrics correspond to functions which are to continuous and PSH functions. And the differences are differences of continuous PSH functions. You don't get any continuous function in that way. You get in some functions so that the Laplacian is a measure. So it's some property with respect to distribution property. That's a property that has to do with suborder spaces or something like that. Okay, and I've over my time, but I don't think I need to say something. Yes, I will just write down an example, but I do not need to be that. And that will allow me to so the example is going back to algebraic dynamics. So the fact that if L is nef, well, say, no, I'm not sure with nef, but I will say with ample. If L is ample, then I can find an algebraic model which is ample. So there exists and then in the existence of Viadic matrix, I had invoked Picard theorem, where I also explained the proof of Picard theorem that starts from a given metric and then makes some process, pulling back, divide by Q, and so on. And so if I start from an ample metric and I start by pulling it back and so on, maybe I cannot pull it back to the same model, but I can pull it back to some other model. But anyway, the new metric I get will remain not ample, but at least will remain nef, or semi-positive. So the limit process that works, that one does in the proof of Picard theorem to construct the Viadic metric preserves the semi-positivity property. So I will take, in fact, I will take a semi-positive. And this implies that it's a canonical metric, adelic metric, is semi-positive. So in this theory, one gets naturally semi-positive metrics if one starts from ample line models. And in fact, it works also if you do not start from ample line models, but it's more subtle. In a recent paper, I mean, recent paper, but a paper that was recently published by Yuan and Zhang, you get a definition they look at this map from peak bar, so metrized line models to line model, and they construct, here you have F upper star, and they prove that this map has a canonical section. So there is a canonical way to define a metric on any line model L, such that on it's pulled back by F upper star, you get the pullback metric. And this is a particular case of that. And those metrics are always admissible and have semi-positivity properties. But I won't name that. This is enough. Okay, so that shows that in the context of algebraic dynamics, there will be a notion of height for subvarieties and with nice functionality properties with respect to F. Okay, I think it's time to stop here.